Okay, thanks a lot for inviting me here, Marco. And this is going to conclude this conference. I hope I won't bore you too much because it is a quite technical presentation. It's not very general, but I've tried to make it as simpler as possible in terms of mathematical content. Right. Okay, we're going to talk about how power electronics converters interact when they are actually included in an electrical network and basically in microgrids, which can be of different kind, and see how we can design control for these power converters in order to avoid as much as possible those interactions. I'm not going to talk about the University of Nottingham and the group because Pat has already done this 2 days ago. I'm just going to introduce this. Thank you. So I'm going to introduce the people who have been working in this project, which is myself, Pat, and Dr. Formentini, another colleague lecturer in Nottingham, and 2 PhD students who have been working on this subject for a couple of years now. So the problem is, when we got power electronics converters into microgrids, or in general into small grids, so in particular with the new integration of distributed generations and renewable energy systems in the power network, and the fact that everybody could be users and producer of electrical energy, the amount of power electronic systems in the network have increased a lot, both for home appliances, for connection of renewable energy systems, for energy storage, for electrical drives. So there are many power electronic systems interacting in the same network. And above all, when this network is very small and is very weak, like in microgrids, we could have this large penetration of renewables and power converters, and several converters operating in the same network. Each converter has its own local control, intelligence and control, but in the end, in an electrical way, they interact on the network. And the complex interactions between control loops require accurate design methods, because when we design a control loop for a power converter to operate on its own, then everything is fine and works perfectly in the lab. And when we put it in an electrical network interacting with other power converters, which they also have their own designed control loops, these control loops and the converters interact, and the performances of our converters does not really reflect what was the initial design. So in the end, we won't have a performance of our converter as ideal as we have designed it for. That is the problem. And this can happen, as I said, I've taken an example in electrical grids now used for distributing energy, but also this happens even in a higher form in other different grids, like, for example, in aerospace, in electrical system for aircraft, for example. Now, we know that, as Pat's presentation also said, there is a tendency to go to more electric aircraft, to include as much as possible electrical systems in an aircraft. And obviously, in including a lot of electrical systems in an aircraft, we also end up to have a lot of power converters interacting in a relatively small network. And in fact, in general, aircraft power systems, this is the example of the Boeing 787, have basically supplied by a fixed voltage variable frequency. So directly from the generators, we have a fixed amplitude voltage variable frequency in general between 360 and 800 Hertz. And from this first distribution grid, we can generate more other AC and DC grid at different voltage level, which by means of power converters. So we have power converters which, starting from a distribution grid, generates these other DC and AC systems. And in particular, I've highlighted this part, which is the 400 Hertz grid, which is main supply to non-propulsive loads like aircraft profile movement or cooling system, fans, window heat, and the environment system, and so on. So everything is fed by this system, 400 Hz fixed frequency and fixed amplitude. And there are a lot of power converters interacting in this network. So in the end, either we talk about aircraft power supply systems, or we talk about microgrids for electrical distribution, the idea is more or less the same. We have a lot of power converters interacting in the same small network. In particular, as an example, we actually started from reproducing as much as possible the possible interaction of converter in this 400 Hz network. The concept can be easily extended to other systems. So this is just to summarize what this project is about. So, as I said, the power converter subsystems tend to interact in an undesired way. In general, the simplest solutions to this problem is use large passive filters between converters. So in this way, if you connect the different converters with large passive filters, you mitigate this interaction between converters. Now, the point is that we can include these filters, but we will increase the weight, will increase the volume of our system, and we decrease the efficiency. So that is something we should be not doing, and we need to find alternative solutions. So the proposed solution is to properly design controllers for these power converters, taking into account all the system dynamics, including the other subsystem where there is possible, in order to achieve an optimal performance across subsystems, mitigation of subsystem interaction, and also we reduce eventual communication needed between different converters by taking into account of the converter at a design level. So, as a notional system, considering, as I said, the possible aircraft 400 Hz supply system, so we started by considering the interaction of only two converters. So a voltage source inverter, which starting from, let's say, here we have actually simplified with a DC supply, but it could be the main variable frequency aircraft power systems. So this voltage source inverter with an output LCR filter provides the grid at 400 Hz fixed frequency here. So generates this 400 Hz nominal frequency grid, and the interaction is considered by supplying a standard three-phase active front end, okay, with an input RL filter, and also as an output we consider either a resistive load, or we could also consider a constant power load if we want to have a more complex situation. So starting from this notional elementary system, we try to see how we can design the controls of these two converters, taking into account of their interactions. Now, I'll try to reduce the maths as much as possible in this presentation. Actually, I'm not going to go into details about the design, the control design. I'm trying to give only the general approach that we've been using. Starting from the voltage source inverter, so when we're dealing with AC system, a common approach is to use a design in the DQ reference frame. So we try to model each of the system in the DQ reference frame. So this means that a three-phase power converter like this one could be described by two average models, one for the D-axis and another one for the Q-axis. Okay, you see here, we say that some generators, voltage generator, which is the DC supply multiplied by the modulation index of the two axes. Modulation index for the d-axis and modulation index for the q-axis. Then we have the RL system here. These generators here actually are representing the interaction between d and q-axis, so the cross-coupling terms, and then the DC, the capacitor part of the system. So in the end, we can write down a state space representation for these average systems. Well, of course, is a general form, so the derivative of the states, which in this case are 4, because we have the currents and the voltages in the D and the Q axis. Then we have the inputs. The inputs in these cases are the modulation indexes for the converter. And also we have disturbances, which are represented by the currents drawn at this point, which will be the currents drawn by the other side, so the other converters. We don't have control on these currents because they are depending on the other converter. So that's why we describe them as disturbances in this approach. So we have states, system matrix, input matrix, and disturbance matrix. Obviously, the outputs are a linear combination of the states as a traditional state space modeling approach for an average system. Same thing we can do for the other converter. So for the active rectifier, which is fed by the voltage source inverter. Same approach, average model on the D-axis and average model on the Q-axis. We have the cross-coupling terms, again, here between D and Q-axis, the RL input filter, and a voltage generator, which is represented by the PD and PQ, which are the modulation indices for this converter, and VDC, which is the voltage, the DC voltage, and the DC side. Here, the state variables are only 3, which are the 2 currents drawn by the D and the Q axis, and the DC voltage here. In this case, the inputs of the system are, as I said, the modulation indexes here. And the disturbances, in this case, are the voltages that are supplied by the VSI. So if we're coming back, are these voltages here. So at this point, on this side, we cannot do anything about these voltages. So these are imposed by the voltage source inverters and considered in here as disturbances. So again, we have a simple state space equation also here, representing the derivative of the states, system matrix, input matrix, disturbance matrix, and the outputs are, again, a linear combination of our states. Okay, so these are the representation of the two systems on an average model. So what we do with this? Of course, now we have to put these two systems together. And what we actually use to optimize the best possible controllers for these two converters interacting between each other is to using H2 control. Okay? So, of course, we have described the state space equations in an average form of these converters. And so we decided to use a multivariable state feedback approach, and in particular, the H2 optimal control. So when we have so many interacting states, so we have described now only 2 converters, but we can have 3, 4, 5 converters. So when we have a lot of interacting states, we've realized the best possible controller are obtained using an approach including an optimal control like the H2 control, which is relatively simple to tune. It is just difficult, well, not difficult, it's just complex to build the model with lots of state variables. But in the end, once you have the model, then applying H2 control is quite simple. Also, has very close roots to robust control, because it uses the Lyapunov function to verify the stability of the system. And there are also versions of this controller that are called H2 H infinity. So there are a lot of different possibilities also to make sure the system is stable and verify whether the system is stable. And also, and more importantly, there are a lot of mathematical software that can be used to automatically tune these controllers. MATLAB has a specific toolbox for H2. And so once we've got all the models set and nicely working, then the design of these controllers using software tool like MATLAB is very simple. It's quite straightforward. I'm not going to go in details about H2 control here. I'm just trying to give the sense of what we are doing. So the approach in general is to have a plant. We have the plant, which is the model we've just described. And in particular, together with the state space equation, which is, as I say, system matrix, input matrix, and disturbance matrix. The output system, which in general is only the C2xt, so we are only a linear combination of the states, but still for generality we have also an influence of disturbances and inputs. And then we have this ZT, which are the performance output, because the H2 control is designed by optimizing a certain system in order to minimize, once chosen these performance variables, the H2 control does the optimization of the gains K to be used in the control by minimizing the possible effect of the disturbance of the system that on these Z, on these performance output. So the approach is to design the value of the gains K in order to minimize the effect of disturbances on some performance output. So we need a model of the system including all the system, including system, performance output, and output. Then we will have the outputs fed back to the inputs using the feedback gains K, calculated according to this approach. This system can be very much reduced in the sense that during the design, disturbances are really generally are neglected. So D11 and D21 are usually set to 0. Also, D22 is the feed-forward matrix. Since we do not assume no feed-forwards in this implementation, even D22 is put to 0. B1 here is this disturbance input matrix. And all state can be influenced by the disturbance. So this B11 can be an identity matrix. So we simplify the system even more. And C2 is the matrix describing the linear relationship between the outputs and the states. If we assume that all outputs are all states, this C2 is also an identity matrix. So the system can be simplified a lot. And finally, C1 and D12 are the tuning terms. I'm not going to go in details on this, but by optimizing, as I said, the influence on the performance output on the disturbance, we can tune the proper controllers for the H2 control. Another thing we need to add is it's important for this system to achieve 0 steady-state errors for the critical control terms. So we are actually adding also integral states for the variable we want to control more precisely. So for example, we are adding integral control for the VC, the voltage at the output of the voltage source inverter, the currents, and the DC output of the active rectifier. So together with the 7 state variables representing our models, we also add 4 more integral terms in order to guarantee the 0 steady state error. The inputs, as I said, are the duty cycles or the modulation indices of the voltage source inverter, which is MD and MQ, and the active rectifier, PD and PQ. So in this way, we have the whole system which has been put together, including DQ representation of the voltage source inverter, DQ representation of the active rectifier. And the total matrix, the final matrix, is given by the two single matrix of the voltage source inverter and the active rectifier, which are AVSI and AFE. And also we have these two matrices, ACV and ACA, which actually considers the interactions between the two converters. So the coupling terms between the two converters. Regarding the inputs as well, we have also the B2 matrix, which is the input matrix, where the inputs are, however, separated because the duty cycles are generated by the control of each single converter, so they don't interact between each other. Now, for the feedback gain, so in the end we get a total system in which we have the control for the active rectifier in the Q reference frame in a classical way, as we know, and the control of the voltage source inverter as well in a classical way with the feedback control of currents and voltages here. And one very important thing that needs to be achieved is when we design this control, we have to make sure, we have to impose that the gains of the control of the voltage source inverter and the gains for the active rectifier are separated. So there are zeros here in these matrices, so there is no interactions between the gains of the single converters. This is something we can achieve and we can include in the optimization of the optimal control. So it's a constraint that we can include in the optimal control. If you do this in this way, we avoid having to consider we consider the interaction at the model level, but then at the control level, we impose to have two separated control, which still takes into account about the system interaction. So we have two separated control, but still taking into account of the system interactions. Right. Then let's go to see some experimental tests on this. This is very new research. There is only a journal being published soon, but there is not much on this yet. So this is the experimental research. The photo has been taken very badly because this looks much bigger than it is because this is on. So these are the LCR filter of the voltage source inverter. You can see voltage source inverter, the AFE converter, and then the controller and the sensors. And as a notional system, we just have built this experimental test in the, let's say, using reasonable values. So you can see the LCR filter of the VSI and the LR filter of the AFE with the capacitance of the DC link side. As I said, the grid frequency, so the grid, the AC voltage generated by the voltage source inverter is at 400 Hertz to emulate an aircraft power system. We are switching at 10 kilohertz both converters with a sampling frequency of 20 kilohertz. So we are using an asymmetrical PWM. So some results here. So you can see that on the left-hand side are some tests for the voltage source inverter. On the right-hand side, some tests for the active rectifier. And you can see that here we have the duty cycles for the VSI. Here we have the currents in the DQ reference frame. The D is the green, the Q is the blue. And we can see that we have very nicely and fast dynamics for this performance. We get at 0.05 seconds, a step of a 1 kilowatt load is applied at the output of the active rectifier. You can see that even the voltage source inverter is affected by this transient that we've put here. But nevertheless, we get a perfect behavior of, the, of both converters. In particular, the DC link voltage here drops only of 13 volts, but it's very, very fast because it is less than 5 milliseconds transient. The voltage source inverter has also a minor transient of just 3 volts, but the grid stays stiff as is expected by a generator. And the whole system performs very well, and because both of systems are taking into account of each other. That is, that the controller is designed based on both systems. One important thing of this approach is the scalability, because we have seen a first approach with only 2 converters, but a general network has more than 2 converters. So we have, can be 3, 4, 5 converters. So the possibility of increasing the size of our matrices by simply adding converters every time needs to be an important feature. And in fact, here we can see we have added a 3rd converter, which is exactly the same as this. So there are 2 equal converters connected on the same AC grid here. And the H2 controller synthesis allows an easy integration of multiple subsystems to the system. It only needs to increase the size of the model, of the matrices of the system. Simply incorporating new systems means expansion of the A and B matrices, and also expansion of the gain matrix K. So we're adding more state variables to the system, are also adding more gains for the feedback control. Still, these gains need to be separated by for the 3 converters. They don't need to be interacting. And so the only constraint we need to add is simply another independent controller for the 3rd converter. But it is simple to add more and more converters on these systems. Now I'm going to show, don't be scared, I'm going to show a very big matrix. Now there is no need of understanding this matrix. It's just to show how the system can be added one by one. And actually, don't be scared. Look at the colors. The blue elements are the 1st converter. The red elements are the 2nd converter. The green elements are the 3rd converter. Okay. So and we can go on like this, adding converters by simply modeling them and adding them to the system. Okay. The thing that I've not mentioned is that for simplicity, these matrices, they don't show the PLLs. Each of these converters, where the 2 active front ends have PLLs. And these PLLs needs to be included in the model of the system because it is a very important part of the system which can influence a lot the converter behavior and above all the stability of the converter when it is in an electrical network. So PLLs are also included in the model even if they are not shown in these state space equations. Now, just to show you the scalability of the system. These are some performance results. As you can see, for the 3 converters interacting, there is always a step load of 1 kilowatt on the active front end number 1 at 0.011 seconds. You can see this first transient. And there's a second transient here, a step load of 500 watts on the 2nd active rectifier and 0.041 seconds, so it's there. So you can see how the inclusion of these step loads really very little affects the behavior of all converters because they are perfectly designed, the controllers are perfectly designed taking into account of all interactions. Okay? You don't achieve this by normal control design. And in order to show this, so as you can see, the systems can run independently. There is very little interaction, and we get very fast dynamic responses. in order to check whether this was really necessary, we have tried to tune PI controllers for all of these three systems. Now, we were really trying, we didn't just design three PI controllers and including them like this. We've tried to design the PI controllers very, very properly to try to make a proper test. And in particular, we have designed PI controllers for this system of course, by normal theoretical design, but also by fine-tuning them with trial and error in order to make sure that we got the best possible behavior achievable with the PI controllers. And these are the best possible behavior we achieve with the PI controllers. You can see, compared to earlier, we get a much deeper variations. These are very good results we managed to get with PI controllers, but still not as good as what we can get with optimal control. In order to tune these PI controllers, we have lost days and days and days trying to really find the best possible behavior. With the H2 control, we spent 2 minutes by simply having MATLAB giving our matrices and MATLAB giving us the gains. So in 2 minutes, we got the very perfect results, and we got days to obtain these results using proper PI controllers, making sure they are perfectly tuned in order to not interact between each other. Okay, so in the end, this is the advantage of using a comprehensive approach for system design when there are lots of converters interacting. If I have a couple of more minutes, I will show this is obviously very nice, but we need to have all information about all converters in the network. So basically, we need to have all converters, knowledge of all converters in the network, which is not often the case unless we are building all the converters. So if we have converters, for example, that they need to be included in the system, in a pre-existing system, so let's suppose we have the VSI, okay, we are including an active rectifier of which we don't know anything about because it is already there, or because another company is building it and we don't know anything about it. So what we do, if the system parameters are not known and the controls are not known, it is possible to operate a system identification of the network. So we can inject some signals from, for example, the VSI here. We can send voltage and current perturbation. We can analyze the transfer function obtained, measured experimentally, and then obtain a state space representation of the system and apply the method we've seen earlier. So this is probably is likely industrial implementation of an H2 decentralized controller. Rather than having all the knowledge of the system, we can obtain the knowledge of the rest of the network by injecting a signal and measuring the impedance. Starting from the impedance of the system, we can reconstruct the state space representation of this system. And in fact, what we've got here is to inject pseudo-binary random signals to ideally stimulate all possible frequency range in the active rectifier. So in this case, we are injecting from here into here and measuring the perturbations of voltage and current at this point. And we obtain here the representation of the admittances. Of course, there are 4 because we are in the DQ reference frame. So these are current and voltage we measure for the signal injection. And we can reproduce from the, you can see that we can, apart from the early frequency here, which are not really interested because we are working at 400 Hertz. And here there is a mismatch until, let's say, 40, 50 Hertz. All the rest, it's very perfectly, very well identified. Okay? So starting from this transfer function of this impedance estimation, we can obtain the state space representation. We can extrapolate the state space representation of this system and then apply the method we've seen earlier without knowing the parameters from the beginning. And in the end, you can see that the blue are the voltage source inverter independently optimized, so by considering only the voltage source inverter by itself. The red is the previous approach when we actually optimize it considering the nominal model, and the yellow one are the results we obtain with the estimation. You can see that the yellows and the red are very, very similar. Actually, the yellow are slightly better in terms of dynamics than the red. So in the end, we can demonstrate that even without the knowledge of exact parameters of the systems, we can estimate only from one converter the rest of the network, calculate a state space representation of that network, and then implement the H2 control. So this is probably the most practical approach that we can show for this method. And that's it. So the H2 control has shown the performance with increased robustness, faster dynamics, and maintain stability and performance under having only small passive filters. So we actually reduce weight and volume of the system, and we increase the efficiency. And also, we have shown that we can apply this method on a larger grid. We can include PLL, we can include all numbers of converters, and we can also implement this system for real application, implementing impedance estimation. Okay, I hope I haven't been not too long and boring with this math. Thank you very much.